Hey everyone, today we're going to be talking about acid-base neutralization reactions, exactly why acids and bases neutralize one another. Now what I've gone here is I've written hydrochloric acid, its chemical formula, and sodium hydroxide, its chemical formula. Now I've put two different parts of them in red, and when you see them in red, I think it's pretty clear as to what the chemistry is going to be in this double displacement reaction. So the reason why acids and bases neutralize one another is because when they react, the acidic part of acid and the basic part of base combine in a double displacement reaction to make water. So HOH come together and they make water, H2O. And the other part of this reaction, right, the sodium and the chloride come together to make NaCl. Now notice I didn't write it ClNa, and that's because when we're doing double displacement reactions, we always put the positive before the negative. So one could think of this as +1, -1, +1, and then the OH as a group is a covalent polyatomic anion that is a -1 in charge. So it's not just on the H or the O, but there's a covalent bond between the O and H, and they carry the -1. And then each hydrogen +1, each oxygen -2, +1, -1. So this is the simplest kind of double displacement reaction here. And there is no additional balancing to do. Now, sometimes you will also have to balance this equation with coefficients in front of the substances, but in here, all atoms are accounted for by this simple double displacement. Also, all of the compounds sum to the charge of 0. Now, acid-base neutralization reactions, right, are said to follow the following form. Acid plus base gives you water and a salt. Now, in our particular case, NaCl is not just any salt, it's called table salt, and that's the salt we put on our food. Salt, though, is really slang or another word for an ionic compound. So, oops, compound. So, salt doesn't always mean NaCl. To common people, it does, sure. But to those of us in the know, salt could mean any number of ionic compounds. So if it is ionic, it is a salt. So if it's made of a positive metal and a negative nonmetal, it is a salt. Let's try another example. What if we have what's called a diprotic acid? What if our acid contains two protons, like sulfuric acid does, and our base will stick to NaOH? Now, in this particular case, right, what you may start to notice already is that it doesn't just make an HOH and H2O, a water. Whoops. Because there's 2 moles of protons in H2SO4. So when an OH combines with one of these H, it makes one water. But what about that second H? Well, when you notice that you have, in fact, 2 protons, you would need 2 moles of NaOH to completely react away both of those protons. And that gives you 2 water molecules. And we still have our salt. Now, the Na here is going to combine with the sulfate. Now, there's a couple different ways you could do this. You could use the cheater method, right? Which is to say to yourself, well, haha, if this was one here and I had 2 of them, shouldn't this be Na2SO4 if it's going to form one compound? And the answer is yes, right? That is kind of like the cheater method. But why is this true, right? Well, if you really start to think about it, our sodium is +1. We've already identified hydroxide as -1. Now, think about the hydrogen, right? +1, but there's two of them. So this whole sulfate group carries a charge of 2 minus. And if you look on the back of your periodic table and you look at the polyatomic anions, you'll see sulfate, SO4, 2 minus, is in that column of -2. So you could also justify it with this understanding and this logic, right? That when sodium, which is +1, and sulfate, which is -2, combine, there's just simply not enough sodiums to balance this whole molecule to a charge of to a neutral charge unless two sodiums, right? Unless two sodiums are incorporated into the molecule. And when we incorporate those two sodiums, right, what we see is 2 times +1 is a +2, and then that's balanced out by the -2 of the sulfate. Now remember, ionic compounds, when they come together to form neutral species. Is there such a thing as triprotic acids? Sure. You know, an example of a triprotic acid would be phosphoric acid, and that is an acid that we find in Coca-Cola. It's not in all sodas, but if you actually read the Coke can, what you'll find is H3PO4 is one of the substances listed in the ingredients. Um, and its actual chemical formula of phosphoric acid is H3PO4. Now, phosphoric acid, immediately when you look at this, has 3 protons. Let's pick a different base, right? Let's try potassium hydroxide. KOH is very similar to NaOH, right? K is a group 1 metal, and so it still has the formula OKOH. It's a 1-to-1, right? +1, -1. Now, again, with a polyprotic acid with 3 protons, we're going to need how many equivalents? We're going to need 3 moles of potassium hydroxide to completely neutralize all of this acid. So we draw our arrow and we make water. And if we used 3 potassium hydroxides, you're going to get 3 waters. And as we write, we put the K first because that's the positive metal, the PO4, and even if you don't use the back of your periodic table, you could figure this out just by looking at it. If there's 3 protons, each of which are +1, the PO4 as a group is carrying a charge of 3 negative. 3 times +1 is 3 positive. What does this PO4 carry? It must carry a 3 negative charge. Now don't get confused with this superscript, the subscript of the 4 there. Unlike unlike binary ionic compounds that are composed of only one metal and one nonmetal, they could be in different ratios. I mean, it doesn't necessarily mean 1-to-1 as in NaCl. You could have iron chloride, FeCl3. That's still called a binary ionic compound because it's made of two different types of elements. But when we look, right, those are two different nonmetals, and this is a polyatomic anion. So just a reminder, when we were learning about ionic compounds, we learned to ignore this subscript when we are figuring out the charges, because as a group, PO4 carries a charge of 3 minus. So let's look at our product to make sure we're done. K is a +1, and if PO4 is 3 minus, we're not balanced. You really must need 3 potassiums when creating this compound so that it has an overall charge of 0. So 3 times +1 gives you 3 positive potassiums, balanced to the 3 negative of the phosphates. And if I go back and I look at each of these, I'm sure that I've got the same number of atoms on both sides of my equation, right? If I wasn't making sure of that, then I'd be violating the law of conservation of mass. So 3 phosphoruses here, right? Plus 3 times 1, which is 6 total on the left. 3 times 2 is 6 hydrogens on the right. 4 oxygens in the phosphate plus 3 more in the potassium hydroxide is 7 O's on the left of my equation. 3 times 1 is 3 oxygens plus 4 is 7. And 3 potassiums on the left, 3 potassiums on the right have balanced my equation. And I've also followed that paradigm that we started with, that, acids and bases, right, create water and a salt. The water, H2O, and the salt, an ionic compound, K3PO4. Now, I'm going to do one more example, probably the hardest you might ever face. What if I took that same acid, H3PO4, phosphoric acid, but I reacted it with a base which has 2 hydroxides? This is neither a simple one-to-one relationship or even a solvable one where you only put one coefficient. You're going to need 2 coefficients to balance this equation. H2O, I still make water, and I'm still going to make a salt, calcium, Ca, and from here I could figure out or use my periodic table. If the hydroxide is -1 and there's 2 of them, calcium, which is in group 2, forms the 2 plus ion. And we know that the phosphate is 3 negative. So the calcium phosphate is not a compound that is simply solved by putting a subscript here next to the Ca. I can't turn a 2 into a 3 with whole numbers, and so therefore calcium phosphate, right, has, oops, I made a mistake. Calcium phosphate has the formula Ca3PO42. And what this also tells me is in order to balance this equation, I must have used 3 of these to give me my 3 calciums, and then this 2 over here is going to correspond to 2 here. I could double check and make sure that I've got everything accounted for, and when I do that, I realize, oops, I'm missing some H's and some O's, right? So I need something in front of my water too, because when I look at this, I have 6 hydrogens on the left, only from here, the phosphoric acid, and I have 2 hydrogens times 3, which is 6, and so 6 plus 6 is 12 hydrogens on the left. I must have made 6 waters. 6 times 2 hydrogens is 12. And I'm going to triple check by making sure my O's all balance now. 4 oxygens times 2 is 8. 2 times 3 is 6. 8 plus 6 is 14 oxygens on the left. 6 times 1 is 6 oxygens on the right. 4 times 2 is 8 in my phosphate. 6 plus 8 is 14 oxygens on the right. So now I'm positive that I've got it right. And the most difficult cases, like this last one, you are going to have to put numbers in front of all of them. So just to review, all acid-base neutralization reactions that we're going to study are reactions that produce water and a salt. So what you'll do when predicting these reactions every time is make sure that water is the first product that you write, and then realize that you're going to be combining the positive of one with the negative of the other, the positive from the metal with the negative of the base after making your waters. And if you add all the signs to 0, just like when we were making ionic compounds, you will get the correct answer.